Video we are going to see about edge detection. So let us see why is it important, what are the different techniques for edge detection, and let's get started. So this is an image. Here you can see that we can see the different edges of the image, and the different edges tell you different things. Like if suppose you see this particular edge, so this basically says that there is a different object that is over here. Say here there is a tree, so this is like edge of depth. So there is something which is not there over here in the 3D world, and hence I can see this edge over here. Similarly, then there is the edge of color. Now this actually is in the same plane, the road. Here there is white color, and then here there is gray color. So there is this edge formed. This is due to the color. So the color change over here is forming this edge, whereas over here you can see it is this tree which is forming the edge. So these are the two types of edges that we see normally in a particular image. So first let us see why edge detection is important. So you can see, say consider this image. Here you can see it is the edge which gives you the perception of shape and the object. So if suppose you see this edge, if you link this particular edge, then you will see a vase, a flower vase. But if suppose you link these edges like this, then you will see a face. So there are two faces over here that you will see. So basically what our brain does is basically it links the edges, and then it finds out what is the shape, and then you get the perception of the object. Similarly, you can see over here, if I suppose link this edge over here, so here I can see a face. These are the eyes, the nose, lips, etc. But if suppose I link this edge, then I'll see a horse. So there are two horses over here that I can see if I link these edges. So that is why edge detection is important, because the perception of shape is preserved in the edges. So these edges basically are the first information that tell us about the object. Also you can see in this image that if I link this edge, I'll see a man who is playing trumpet or some instrument over here. But if I link this edge, then I can see a girl's face. Here in this image you can see there is nothing over here till my brain is linking these edges, and you can see a star that is formed over here, but actually in reality there is nothing that is over here. But then you can see that there is something that is forming, that is like it is a kind of an illusion that the brain wants that there is a line over here. So hence it is very important to detect these edges while doing image processing, and we are going to see how we can do this. So consider this is an image. So this is a very simple image, black and white image. So here you can see this is an edge. So this is the whole image, and here there is a edge, that is the color difference. Here there is white, and suddenly abruptly black starts. So if you see the matrix, the image matrix of the corresponding image, it will be something like this. There will be 255 values for white, so all 255 values over here, and then suddenly there will be all zeros. So basically what our aim is to detect this edge, because the edge has a lot of information in it, as we have seen earlier. So our main motive is to just detect this edge, and I will do that. So here if suppose we have some algorithm that can find the difference of the neighboring pixels, then your job is done. Say consider this particular portion of the image, and say if I do 255 minus 0, so I get 255. So let there be some imaging some tool that will subtract the edges, subtract the pixels, the neighboring pixels. So if suppose I am considering this image, say I am considering this particular pixel. So what will I do is I will do the left pixel minus right pixel, suppose. So 255 minus 0. So this answer will come as 255. The same will come over here. So this whole line I will get 255, 255, 255, 255 on this whole line, because everywhere there is 255 on the left and 0 on the right. So I will get high values, 255 all over here. But if suppose I do the same thing on this line, so I'll get left minus right, so 255 minus 255, so these all will be 0, 0, 0, 0, 0. So can you get it? It is just there. If suppose we devise an algorithm that takes the difference of the neighboring pixels, then we will be able to detect the edge, and that's exactly what we are going to do. So that's exactly what we are going to do over here. So these are the different edge masks that we have. So there is this Roberts mask. So this Roberts mask is a little different type of mask. So edge linking is basically like the low pass and high pass filtering in image domain that we have seen. We have seen a low pass mask, we have seen a high pass mask, the averaging mask, etc. So the same logic is applied over here, only that the mask is different. So here you can see this is the Roberts mask. So what this particular mask will do, it will subtract the pixels diagonally. So in this case, what will happen if I put a Robert mask, it will do this 255 minus this 255, which will give you an answer that is 0. So this 255 minus 255 is 0, so the result will be stored over here. But then if there is an edge, say this is an edge that is detected over here, so then it will do 0 minus 255, which is minus 255, but then it is giving a value. So in this way the Robert filter detects the edges. Similarly, this is the pivot mask. This was what I was explaining. So here you can see that this is an x derivative and there is a y derivative. So why is this? So here you can see this is a edge in the y direction. So for that edge we required a mask which does what we say, left minus right. If suppose this edge would have been like this in the horizontal direction, then we would want some, say suppose here there was a value, say 255, say this is 255, this is 255, this is 255. So here you can see that there is a horizontal edge. So for the horizontal edge we will require a mask which does up minus down or down minus up. So in this way we can have two types of masks. We can have an x derivative and a y derivative. So similarly there is an x detection mask, there is a y detection mask. Okay, talking about Sobel basically gives priority to the 4 neighbors. So here the priority is equally given to the diagonal, say considering this as the seed point. So these diagonal neighbors and the 4 neighbors have equal priority. Both are 1, 1, 1. The biases are the same. But here in the Sobel filter you can see that the diagonal the four neighbors have been given more priority as 2, and the diagonal neighbors have less priority, that is 1. We will see what difference does this make in the further slides. So first, talking about pivot. So here, say, consider this image of a chess board. So here you can see when I apply the mx, when I apply the x particular derivative of pivot, so what will happen is it will give me these horizontal edges only. So here you can see these horizontal edges are seen over here. So basically these some are dark and some are light. That is just because there is this black and white thing over here. So wherever there is a black, it is giving a little lighter shade because the lines and the color is the same, and wherever there is white, it is giving a darker shade. That is it. But it is detecting the edges quite nicely. Also, if you see the y derivative, so here you can see the let me name this image as my. So here you can see that it is detecting the vertical edges. So here mx is detecting the horizontal edges by this particular mask. So I will apply this mask on the image first, and then I'll get this answer. Then I will apply this mask on this image and I'll get this particular thing. But then actually I want the total edge detection. I don't want the x and y different images. So for that we will have to take the magnitude. So for taking the magnitude, we have this basic formula, that is square root of mx square plus my square. That is the main formula for taking magnitude of any x and y thing. So here the same formula is applied. So what we do first is we take the image, we put the x filter on it, we put the y filter on it, we get two different image, mx and my, and then we take the magnitude by this formula, root of mx square plus my square. That's it. So this is the final edge detection output. So you can see how clearly the edges are detected over here. We will also write a program in MATLAB in my MATLAB tutorial video in my upcoming videos. So we will see how this particular images are formed. That we will also see in my upcoming videos. Also here I will tell you the difference between Robert, Privet and Sobel operators. So let us see why are these three different operators used and what are the differences in between them. So here you can see this is an image. So if I apply Robert's mask on this image, I get this particular output. I have directly taken the magnitude. So this is the magnitude. I have done mx my square and taken the root of it. So I have taken the magnitude over here and I get this particular kind of image. So here you can see that the edges are thin and the brightness is less. So basically the edge values are little less. So wherever you want to detect the thin edges and you don't want to detect many edges, so here you can see it is perfectly detecting this particular face. Here it is not detecting this particular part. The eyes are detected, the lips are detected nicely. So where you don't want many details, you can use the Roberts filter or the Roberts mask. This is the original image. Okay, now if you talk about the Privet mask, so here in the Privet mask you can see many details are included in this particular detection. So here you can see the hairs are also detected, the face is quite nicely detected, the eyes are very nicely detected, the lips is detected. So basically the Privet masks is a better detector than the Roberts mask, but then it depends on what do you want to detect. Now this detects a lot of things, like over here you can see this can be said as noise, but then because it is her hair, so it will have to detect all those things. But then if you don't want to detect these things, you can use the Robert filter to detect only the eyes or the lips, depending on what is your application. Now in the Sobel mask, you can see this is a even better output as compared to the Privet mask, as here you can see the brightness is more. Here the eyes are more perfectly detected as compared to the Privet mask. So all of these are magnitude. I have applied the X mask first, then the Y mask, and then taken the magnitude. So I'm just showing you the magnitude over here. So this is the difference, basic difference between the Robert mask, the Privet mask, and the Sobel mask. So on a basis of your application, you can decide which mask do you want to take, and correspondingly you will get an output. Okay, coming to some more images. So here you can see this is a image of a sun. So this is a very beautiful image of the sun. So here you can see when I take the mx and my, it gives me these outputs, and this is the magnitude. This is the magnitude. So here you can see in this magnitude that this particular ring is not detected. So this I have used the Privet masks for detecting this, but you can see that the ring is not very nicely seen over here. This ring that you can see over here. So sometimes the magnitude does not give you a nice estimate of all the edges. Sometimes some edges are left out. In case you want to detect this particular ring, then that is not very easy in the magnitude operation. So in such cases we go with the angle operation. So here what I have done is, I have, instead of taking magnitude, I have taken tan inverse of my by mx. So initially in magnitude I used to use this formula, that is root of mx square plus my square. Here by taking the angle, what I have done is I have taken tan inverse my by mx. So not only this, after doing tan inverse, so basically this will give me an angle. So the angle will be in between 0 and 360 degrees. So what I have done is I have taken a particular color scheme and I have allotted the different pixel numbers to the different colors over here. So 0 is considered as black, because 0 means that there is no angle, basically no edge over there. So all these here you can see, here there are very little or no edges over here. So this is what is seen over here. But the beauty of the angle is you can perfectly note out the ring that is formed over here. You can see in the magnitude it is almost invisible. The ring is almost not visible in the magnitude, but in the angle you can very beautifully see the ring of the image, the original image. So this is what we have done. So in when you want to do precise detection, there is some information that is stored in the magnitude and there is some information that is stored in the angle. So both of them are useful when you are doing the edge detection. Also here you can see this is a very nice artist impression of black hole. So when I take the magnitude of this image, here you can see that these these twirls and this particular texture is lost. This texture is totally lost, and I can see the stars and all those things very clearly. All these dots are very clear over here. All the stars are very clear, but then this texture is lost. While the same thing, when I take the angle, here you can see the beautiful texture that is seen over here. So this texture is all preserved in this angle. So whenever you want this texture information, you can go for the angles. So here those textures will not be available. So in that case you will have to go for the angle. Also here you will not see the stars. So these different stars that you want, that information is not provided in the angle, but then that information is there in the magnitude. So the magnitude and the angle, both of them are equally important over here. So this was about the edge detection. The main part that is detecting the edges are these masks. So basically these masks will tell you what particular edge output you will get. So that was all for this video. Thank you so much for watching. Thank you so much.